Welcome to this webinar where we look at loss budgets in the FTTx systems and how they impact configurations and architectural decisions. In FTTx systems, there are three key architectural components that decide the allowable length of the optical link. Primarily the fiber optic cable. The various fiber optic cable manufacturers may have similar loss characteristics, or they may be quite different. Spectral attenuation is where in a given manufacturer's cable the loss or attenuation of a signal is a direct correlation between the wavelength and the distance. So when increasing the split ratios from 1:32 to 1:64 and higher, the spectral attenuation becomes very important. Another factor that needs to be considered is that as fiber optic cable ages, the attenuation increases due to the phenomena of hydrogen aging. This is where the molecules of hydrogen atoms in the silica or glass tend to break down over time, making the fiber less clear to transport the light pulses. The second component is the class of optics. Within the standards bodies, various classes of the optics electronics are defined. EPON has traditionally used Class A optics, but have moved to the Class B optics and fall within the BPON specification of split ratios to 1:32 and distances of 20 kilometers. GPON utilizes Class B plus and Class C plus optics. The third component that is affected is split ratios. Let's discuss these in more detail. The spectral attenuation is simply the loss characteristics built into the fiber optic cable given a particular optical wavelength. The lower the wavelength, the higher the spectral attenuation. You will see this applied to link loss budget calculations where we will take the worst case and apply those numbers for the end-to-end loss budget. Shown here is the fact that after the 1600 nanometer wavelength, the intrinsic attenuation actually goes back up. Therefore, it is not logical to say that we can keep extending the wavelength to achieve lower and lower losses. PON equipment generally operates in the ranges between 1310 and 1550 nanometers. When applying to distances and calculating the link loss budget for a given architecture, fiber optic cable manufacturers must specify the spectral attenuation for their products. In designing the FTTP network, the design engineer will initially design for the wavelength with the highest loss characteristics. The loss will vary from manufacturer to manufacturer. When we start increasing the split ratios in a given network, the spectral attenuation will be closely monitored. Optical link budgets are determined by individual vendors' active components, PON chips within the electronics, the lasers, and receivers. The PON optics classes have been defined as Class A, B, and C, and looking at traditional BPON equipment, this has always used the Class B optics with a link budget set at 25 dB. It was determined that some of the PON networks of 20 kilometers were actually stretching these budgets to the limit, so the active equipment manufacturers were forced to increase them to 26.5 dB. With the advent of these increased budgets and the possible need to increase the split ratios of GPON, the Class B optics were given an increase in the receiver photodetectors to allow for a 28 dB loss budget. While still not in the Class C optics range, these components were given the distinction of Class B plus optics. The key differentiation is that the cost of these Class B plus optics have not increased to the Class C pricing while maintaining better PON loss characteristics. This is not to say that in the future the need to transport to longer reaches, say 30 or 40 kilometers, and even higher split ratios 1 to 128, will force the equipment manufacturers to the Class C or C plus optics. Splitters are passive devices because they require no external energy source other than the incident light beam. They are broadband and only add loss, mostly due to the fact that they divide up the input downstream power. This loss, called splitter loss or splitting ratio, is usually expressed in dB and depends mainly on the number of output ports. It should be noted that contrary to what one might expect, the splitter adds approximately the same loss for light traveling in the upstream direction. Regardless of the splitting architectures or PON technologies used when calculating the link loss budget, you need to account for the splitter loss configurations as shown. These losses include connectors and are the maximum defined by the International Telecommunications Union ITU G.671 and Telcordia GR 1209. The network design engineer does have some options to lower the loss, though, by using premium splitters and low-loss connectors in the network, and to ensure that fusion splices are well below 0.05 dB per splice. Optical link loss should be calculated using the manufacturer's hardware specifications, the actual link distance, optical split ratios, and link losses from all connections. These losses must not exceed the optical budget allowed for the particular system electronics. Keep in mind a 3 dB loss margin is always a good practice for a long-term reliable optical network. This buffer of loss margin is designed to tolerate not only the environmental effect and the lifetime effect on the passive optical network, but also that of active electronics. The OLT-ONU transceiver link budgets were listed previously based on different classes of optics. As stated, one of the primary loss factors is the fiber cable attenuation, which is the decrease in the strength of the signal as it passes through the fiber. This is measured in decibels per kilometer. The amount of attenuation occurring in a given fiber varies according to the wavelength of the light. In practice, the aim is generally to have attenuation as low as possible, because that means we can transmit further before the power of the output signal drops so low that the receiver can no longer detect it. This table provides information on the loss factors for fiber cables and connectors which must be accounted for, including upstream and downstream link pass. Note that the ONUs also have a maximum receive power. If the distribution fiber does not have enough loss, for example, does not run through a splitter, then an inline attenuator may be needed to avoid damaging the optics and ensure the power is within the receiver limits. As connections and/or splices are added to a link, these add a loss per connection as shown. As most architectures incorporate passive splitters, these need to be added to the link loss. This example shown has only one splitter and would be where the PON is serving a group of subscribers in a fairly remote area. Here there are two splitters in the link, so the loss just from the splitters will be double what we saw in the previous link. There are still the same number of other connections, so the attenuation is calculated per link from the central office to the subscriber's ONU, and each will be different due to the actual length of the fiber in the channel. With this link example, we now have a problem, as our optical power budget power has been exceeded. This is why precise calculations need to be made in the design phase, and also that the loss limits of the connections are not exceeded by the field engineers. Let's now consider a few examples. As we've seen in the previous lesson, PON can be deployed using a number of different architectures. The centralized split architecture employs a single splitter for each OLT-PON port. Based on the location of the OLT and the end-user groups, one or more multi-fiber cables may be used to connect the OLT-PON ports to each splitter closest to the end-user groups. The example shows a single 1:32 ratio splitter where the link loss will be the loss of the 1:32 splitter plus fiber cable and connections. Assuming a 20 kilometer fiber cable from the OLT to the ONU and 4 pairs of LC APC connectors in the link and 10 splices, then the link loss would be as follows: 6.8 dB for the fiber, plus 1 dB for connectors, plus 0.5 dB for splices, plus 17.5 dB for the splitter. This equates to a loss of 25.8 dB, which is within the PON optical budget. In this distributed split architecture, the OLT is located in a data center or other distribution point. At the first split, the trunk cabling is divided into multiple runs, each to a separate user group. Once close to each user group, the signal is split again in order to feed the individual ONUs. The cascade of splitters with different ratios provides great network design flexibility and reduces the fiber counts in the cables. However, the link loss calculation has to take the losses of both splitters into consideration. Using the above example, assuming the total fiber cable length from OLT to ONU is 20 kilometers and 6 pairs of LC APC connections and 12 splices, the link loss is calculated as follows: 6.8 dB for the fiber, plus 1.5 dB for connectors, plus 0.6 dB for splices, plus 18.5 dB for the splitters. This equates to a loss of 27.4 dB, which is just within the PON optical budget. Another example here is a typical architecture covering an MDU or multi-dwelling unit environment where the OLT is located in the central office. The trunk cable from here is spliced at a fiber optic splice closure from which a number of fibers are diverted down to a mini FTTH fiber distribution hub in the basement of the building. In the FTTH, the signal is split to feed several network access points, or NAPs, which are closures that allow local administration and connection. Drop cables are used to connect the FTTH to the NAP and from the NAP to the ONUs within the apartments. Using the above example, assuming the total fiber cable length from OLT to FTTH is 10 kilometers and 4 pairs of LC-APC connections, 2 splices, and 100-foot drop cables, the link loss is calculated as follows. 3 dB for the fiber, plus 0.8 dB for connectors, plus 0.1 dB for splices, plus 16.5 dB for the splitter, plus 0.05 dB for the drop cable. This equates to a loss of 20.45 dB, which is well within the PON optical budget. In this last example, the diagram shows typical architecture covering a single-family unit or SFU environment where the OLT is located in the central office. The trunk cable from here is spliced at a splice enclosure from which a number of fibers are diverted down to the FTTH fiber distribution hub located in the local community. In the FTTH, the signal is split to feed several network access points, NAPs. Drop cables are used to connect the FTTH to the NAP and from the NAP to the ONUs within the residences. Using the above example, assuming the total fiber cable length from OLT to FTTH is 15 kilometers and 5 pairs of LC-APC connections, 3 splices, and a total of 750 feet of drop cables, the link loss is calculated as follows. 4.5 dB for the fiber, plus 1 dB for connectors, plus 0.15 dB for splices, plus 16.5 dB for the splitter, plus 0.38 dB for the drop cable. This equates to a loss of 22.53 dB, which is again well within the PON optical budget. That completes this webinar. Thank you.